So today we want to talk about what's called expected value. Okay, so last time we talked about the concept of a discrete random variable. And, you know, the discrete random variable is nothing very fancy. Basically, it said we take an experiment, and from that we derive a number, okay? So now everything that we do in this class is going to be numeric, right? So now that we're dealing with numbers, we can start to characterize the properties of distributions, for example, numerically, right? Whereas it might have been difficult to do that before when the outcomes might have been somewhat like symbolic, okay? And so the key concept from last time was what we call the probability mass function. I'm going to write this down in full, but we abbreviate this as a PMF. Right? So if I have Px of k, that's the probability that the random variable x takes on the value k, right? So for example, say I, flip a coin 3 times, then my probability mass function looks like, in 3 flips of a fair coin, okay? So I have possible outcomes 0, 1, 2, 3, and the probability of each of these outcomes is 1/8 that I get 0 heads, 1/8 that I get 3 heads, and then it's 3/8 that I get 1 head, 3/8 I get 2 heads, right? This is one example of a binomial distribution, right? So another thing we did last time was we gave a bunch of things that we had done before some new names, right? We talked about the uniform distribution, the geometric distribution, the binomial distribution, and the Poisson distribution, with the understanding that any set of these, bars or arrows that adds up to 1 is a valid PMF, right? So it doesn't need to be one of these special distributions to be a valid PMF, okay? And so now we want to talk about a way to kind of concisely summarize some important properties of these distributions, right? And the most immediate one is what's called the expected value. So the expected value and sometimes you also see this called the expectation or the mean or mu. All these numbers basically kind of mean the same, all these terms kind of mean the same thing. The expected value of a random variable it's basically a weighted sum. So basically it's defined as this. Expected value of x, we use this big E. What we do is we sum over all the possible values k times the probability that x takes on that value, right? So it's basically like the sum of the possible values weighted by their probabilities. So for example, in this picture I just drew on the left, what's my expected value? Well, I have 4 possible outcomes, right? 0, 1, 2, 3. Each of those has different probabilities. My expected value is saying, okay, I take 0 times the probability of getting 0 plus 1 times the probability of getting 1 plus 2 times the probability of getting 2 plus 3 times the probability of getting 3, right? So that's equal to 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. So I add this up, I get 3/8 plus 6/8 plus another 3/8 is 12/8, right? So that's going to be like 1.5, right? And so, this kind of makes intuitive sense, right? Because 1.5 is kind of the middle of this distribution, right? So that kind of makes sense in the intuitive sense of kind of an average, right? Now, let me just say that the expected value is not the same as the most likely thing to happen, right? That would be what we call like the mode of the distribution. So maybe you remember vaguely from high school, you learned about the average of a set of numbers, the mean of a set of numbers, the median of a set of numbers, the mode of a set of numbers, right? So here we're talking about the mean of a set of numbers, kind of, right? So let us write that down. So E of x is, not the same as the kind of most likely outcome. And it's usually not an outcome at all, right? So for example, here, the expected value is 1.5. I can't flip a coin and get 1.5 heads, right? That's not one of my possibilities. Instead, the way I think about this is that the expected value is kind of like the long-term limit of what I would get if I saw a whole bunch of experiments, right? So basically, think of it like this. Think of it as the kind of limit of the sample mean. That is the average over many, many, examples or trials, right? So for example, in this flipping case, the sample mean would be like, I take the number of trials where I observed k heads over the total number of trials, and every time I saw that, I got k. And I want to add those all up, right? Let me actually maybe do this in MATLAB for a second just to kind of show you what I mean, right? So let me actually use MATLAB to do some mock coin flipping, okay? I'll come back to this page in case you're still copying it, but let me go to the computer for a second. So suppose, for example, that I want to take a binary random variable, or I'm sorry, a binomial random variable. So let's say I'm going to make a vector that says a binomial random variable that has 3 coin flips and a probability of 1/2 getting a head. And how many of these do I want? Let's say I make 1,000 of these, okay? So I'm going to make a 1,000 by 1 vector of these, right? So now what I have is a length 1,000 vector v, and if I look at the first few entries of this, these are just the number of flips that I got in these experiments. So a lot of the time you can see I'm getting 1s and 2s, and I'm not getting 0s very often. I didn't get any 3s at all, right? And if I were to look at the average, or first of all, let me look at the, let me look at the histogram of this v over my possibilities, right? So this is kind of like the bar graph of what did I get, and you can see that it kind of looks like my ideal, binomial distribution, but in this case I got, a few more 1s than 2s, and, but it still roughly looks like the right thing, right? And if I were to actually look at the counts of these things, right? So if I were to look at the number of things in the bin, I'd see I got, out of 1,000 flips, I got 127 where I got 0 heads and 121 where I got 3 heads. Both those numbers are pretty close to the ideal value of 125, right? So if I look at the mean of these flips that I get 1.47, which is pretty close to the 1.5 that I just computed on paper, right? So that's what the expected value kind of is what is my, expected average outcome, right? And so, again, if I were to do this a lot more times, so if I were to do this, say, 100,000 times, and then look at the mean, I'm even closer to 1.5 than I was before, right? Okay, So let me flip back to my document camera here. So basically, as the number of trials goes to infinity, the sample mean approaches the expected value. Okay? And so it's not hard to do some basic computations about what is the expected value for the stuff that we learned about so far. Okay, so let me pause and ask. Questions or comments? Okay, so let's go back and do the random variables we learned about last time, right? How would those expected values be computed? Well, let's do some examples. Well, the first one we talked about was the Bernoulli random variable. Remember that that was very simple. Basically, it said that I have probability 1 minus p of getting 0 and p of getting 1, right? This is just like a binary random variable, one coin flip. And so the expected value of this Bernoulli random variable, it's going to be 0 times the probability of getting 0 plus 1 times the probability of getting 1. So it's just p, right? And that kind of stands to reason, right? So, you know, for example, suppose that I gave you, you know, $1 every time you played this, every time you play this game and get a 1, I gave you $1, right? So how many dollars would I expect to get after, you know, playing 1,000 games? I would expect to get 1,000 times p, right? That's kind of the fraction of how many games are positive, how many successes I've got, right? So that's super easy. How about a geometric random variable? Right, so geometric random variable looks something like this, where I have a p chance of succeeding on every successive flip, and so on, right? So this is the one that we were talking about on the last homework. So let's remember that the PDF of this thing is basically, you know, I have to fail k minus 1 times and succeed on the kth try. And the possible values are 1, 2, 3, off to infinity, right? Well, let's figure out what my you know, expected value is. Expected value then is going to be the sum over all of my possible outcomes, that outcome times the probability of getting that outcome. And now I'm going to plug in what I know about the PDF. It's going to be the sum from 1 to infinity of k times p times 1 minus p to the k minus 1. Now that looks like a mess. But let's find out how we can simplify this, okay? So I can take the p out. So let me just take that out. So I've got k times some number to the k minus 1. So let me make my life a little bit easier. Let me just kind of do a sidebar to make it a little bit easier to see what's going to happen. So if I have k times some a to the k minus 1, right? So a is just some number. Let's think about what does this mean, right? This is like saying I have, you know, 1 times a to the 0, which is 1. I have 2 times a to the 1. I have 3 times a to the 2, and so on, right? So that's the kind of series that I have to sum up. And I can break this up a little bit. I can say this is actually the same as, you know, suppose I have 1 plus a squared plus a cubed. That's something that we know how to do, right? That's the formula that you keep on working on, the geometric formula. So that's part of what we know. Now, if I want to pick up the next a, I can add like this. So now I've got 2 a's. Now I need to pick up an extra a squared, and I can get this, right? And each of these guys looks like a geometric thing on its own, right? So the first one looks like 1 over 1 minus a. That's the geometric random series. This next one is exactly a times the same thing I have on the top, which is 1 over 1 minus a. The bottom one is a squared times the thing that I have on the top, and so on. And then I can say, well, look what this is. This is like 1 plus a squared plus dot 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 times 1 over 1 minus a. And hey, this thing is actually, again, 1 over 1 minus a. So it's 1 over 1 minus a squared. So what did we learn? We learned that this infinite sum corresponds to this value. Now, what have I got coming back to my case, right? So if I kind of come back to what I have p times this infinite sum where the role of a is being played by 1 minus p. So I have 1 minus p squared. This thing in the denominator is just another p. So I have a p, I have a 1 over p squared, and the big result is that I have the expected value is 1 over p. Now, don't worry, you're not going to have to do this kind of thing on the exam, right? This is just kind of like a derivation of a property, okay? I like to kind of show you where these things come from. It's good mathematical exercise, right? But the key idea is that, you know, again, to kind of draw it all together, for a geometric random variable, the expected value is 1 over the probability of success. And what I want to just dwell on is why that makes sense, right? So if the p is high, right? So if the probability of succeeding is pretty high, then the expected value is low, right? That makes sense because if it's likely for me to succeed, then on the average, I don't think it will take me that many tries to succeed, right? But suppose p is really small, like say p is 0.01, very, very unlikely to succeed, then the expected value is 1 over that, which is 100, right? So it is likely that it will take me many, many, many tries to succeed. So it kind of makes sense that there's like this inverse relationship between the probability of succeeding and the expected number of tries I have to have, right? So let me pause and ask questions about this. Okay. So let's do one more along this line. And let's do the Poisson, right? So let's suppose that x is Poisson. We learned that one last time with the parameter alpha. So our PMF that we talked about last time is alpha to the k over k factorial e to the minus alpha for 0, 1, 2, and so on. So what's my expected value of this? Expected value of x is, it's the sum from k equals 0 to infinity of the value that I could get times the probability that I get that value. Now again, this doesn't really look like a lot of fun, but I can take an e to the minus alpha out. I can see that the k equals 0 term doesn't really matter because it's being multiplied by 0, so I'm going to renumber my sum to go from 1 to infinity. And then I have basically alpha to the k, and then this k cancels with this k over here to give me k minus 1 factorial. Now what is this thing? If I just were to write it out, right? So when k equals 1, I get 1. Let's see, hold on a second. What did I miss here? Oh, I missed, there's a k minus 1 here. I have to renumber this. What did I do? Alpha to the k is good. Alpha to the k is good here. Oh, I'm going to take an alpha out of here too. I'm going to take an alpha like this, and then I'm going to drop this guy down one. So I keep an alpha on the outside. Okay. So now what I have inside the sum, when k equals 1, I have alpha to the 0, which is 1. When k equals 2, I get alpha by itself. When k equals 3, I get 1/2 alpha squared. Then I have 1 over 3 factorial alpha cubed plus dot, 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 right? Now this here, in the midst of your calculus memory, should register as what you called the Taylor series for e to the alpha, right? So this is basically just like the Taylor expansion of e to the alpha. And so what I have is alpha e to the minus alpha e to the plus alpha, which is just alpha. And this, so the upshot is that the expected value of the Poisson random variable is alpha, the parameter that we chose. And that makes sense because that's actually what I told you in the first place was the meaning of this parameter, right? The alpha is the average number of things that I expect to happen, right? And that's exactly what we got, that the average number of things turns out to be the alpha. So everything is good. In some sense, it's kind of like a roundabout way of just telling you that's, why we called alpha the expected value, okay? Okay. So I know this is all kind of abstract with symbols and equations. Let's make this a little bit more concrete, okay? So let's do some examples with some actual numbers, okay? Now, a very common thing to want to do is a expected value of some function of a random variable, and that's what I'm going to do now and give you some numbers, okay? So we often want to compute the expected value of a function of a random variable. Like, let's call that function g of x. So I do my experiment, I get my numerical outcome, and then I apply some function to that, right? So here's an example, again, back with the coin flips, right? So suppose that we're flipping the coin, and I am going to offer you to play a game, a super exciting game, right? So if 0 comes up, I'm going to give you $0. If 1 or 2 comes up, I'm going to give you $1. And if 3 comes up, I'm going to give you $10, okay? And so the question, and you see this in probability, textbooks all the time, is, how much should you be willing to pay to play this game? Okay? That's like a very standard way of seeing a problem written. So how much should we be willing to pay to play? Right? Because if the, price that you're paying to play is less than the expected value, then on the balance, you're going to lose, right? And this is exactly the premise of all the bets in Las Vegas, right? So all the bets are set up in such a way that the amount that you have to pay is more than the expected value of the winning, so that the house is always getting a little bit of an edge, right? And the difference between the amount you pay and the expected value is the house's cut, right? So that's the whole premise behind all the gambling. And so that's why people who are interested in gambling as a science, they look for the, the bets that have the smallest difference between, the smallest margin, right? So let's look at the expected value for this game, right? So the expected value for some function of x is defined in just the same way as the way we defined it for just regular expected value, right? So it's like saying I look at the possible outcomes that I could get, I take the probability of getting that outcome, and I multiply it times that function, right? So for example here, the expected value of my payout it's like saying, okay, with probability 1/8, so let's remember what these probabilities were, right? So the probabilities of each of these values was 1/8, 3/8, 3/8, 1/8, right? So it's like saying, okay, I'm going to give you $0 with probability 1/8. I'm going to give you $1 with probability 3/8, and another $1 with probability 3/8, and I'm going to give you $10 with probability 1/8, right? So what do I get? I get 3/8 plus 3/8 plus 10/8 is 16/8, which is $2, right? So you should be willing to pay at most $2 to play. Otherwise, on the average, you're going to come out behind, okay? So we should be willing to pay at most $2. So questions about this example? So let me take one step back and just kind of like be really pedantic about what's happening here, okay? So let's kind of think about this in a very step-by-step way, which is like saying, okay, you know, I have kind of like my original, how do I want to draw this? So I've got my original sample space for the actual experiment, right? Up here, I have, you know, basically 4 sets that partition the sample space, right? I've got tail, 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 head, 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 and I've got one head, and I've got 2 heads. Now, each of these sets in the original sample space maps down onto a number, and the number is our random variable. So this is like the sample space for x, right? So this maps down to 0, this maps down to 1, this maps down to 2, this maps down to 3, right? And then I further have some sort of function of x that says, okay, well, now I'm going to have $0, $1, and $10, and this guy goes to 0, and these guys both go to 1, and this guy goes to 10. And that's just like saying, okay, suppose that I had just kind of like you know, I could have just kind of thought about a different way of sucking up the sample space into sets where, you know, this is the outcome that leads to 0, this is the outcome that leads to 10, and then, you know, this is all the other stuff. Right? So I could think about like saying, okay, this maps to 0, this maps to 1, this maps to 10. So the reason that this works is that, you know, I could have kind of removed the intermediate experiment and just said, I've got a new random variable for you, right? And I don't even have to worry about the number of heads. I just tell you, here's a mapping from the sample space to the real line, and then you can compute the expected value of this thing directly, right? So again, this is kind of like really pedantic, but it kind of shows why this definition is okay. Okay, so let me just kind of talk about some important properties of random variables, okay? So I'm going to ask you to compute a whole bunch of expected values in this class and in many future classes, right? But you can use some nice properties that make life easier, okay? And so these properties may somewhat be familiar to you from, for example, when you took signals and systems, you were talking about like linearity, right? Linearity was this kind of important concept in signals, and you probably have had that by now if you're taking signals at the very same time as this, right? That's probably like lecture 3 or 4 of signals, right? So the nice thing is that this expected value function is, you know, linear in the same way, right? So properties of expected value right? So let's suppose that I have the expected value of a constant, right? Expected value of a constant is just that constant, right? That makes sense because it's like no randomness, right? It's like a PMF that has one arrow that has height 1 centered at C, right? So there's absolutely no uncertainty about what happens. So I can basically just like move the constants out of my expected value computations. And so that means that the expected value of x plus a constant is just the same thing as expected value of x shifted by that constant. Also, the expected value of, you know, some function of x plus some other function of x is just the same as separating these guys out. So I can split up sums within the parentheses and bring them outside the parentheses. And if I have like expected value of ax, where a is, you know, some real number, that's just a times the expected value of x, right? So the expected value of 2x is the same as 2 times the expected value of x. So what all this means is, you know, the expected value, or this expectation operator, is what's called linear, meaning it kind of behaves in this way, right? So that linear is kind of a tie back to why we talk about probability and signals in the same kind of semester, right? So this allows us to take things that seem very complicated and make them a lot easier, okay? So you'll notice that, you know, I talked so far about computing the expected value of the Bernoulli, of the geometric, of the Poisson. Our old friend, the binomial, right, the one that we keep on talking about, I didn't talk about yet. So let's talk about the expected value of the binomial distribution. So let's say that x is a binomial random variable. What is the expected value of x? Well, let's remember that the mass function, the PMF, is saying I take n choose k, then I have k successes and n minus k failures, and k can range from 0 to n. So the expected value then should be the sum, my possible outcomes are 0 to n, k times n choose k, p to the k, 1 minus p to the n minus k. So this looks like a nightmare, right? Like, how am I ever going to simplify this, right? Not easy to do, and I'm not going to attempt to do it, right? What I'm going to observe now with my newfound linear power is that we can think of x as the sum of n Bernoulli random variables. Right? So it's like saying I'm going to, instead of talking about the sum of the flips as an aggregate, I'm going to say, well, I have n separate random variables, each one of which is a coin flip. And I record success or failure on each of those binary random variables. I add them up. That's the same as the binomial random variable, right? And so that makes life much easier, right? Because if I say now the expected value of the binomial is the expected value of the sum of these n kind of sub-random variables, I can break this sum up because I just talked about linearity. And each of these guys has the same expected value because each of the flips is independent and identical. And we talked about in an earlier slide, the expected value of the Bernoulli random variable is just the probability of success. This is kind of from before. And this is like much, much easier, right? So basically, the expected number of heads in n coin flips is like saying it's n times basically the probability of getting a head, right? That kind of makes intuitive sense. So I didn't have to go and try to use some crazy calculus to try to resolve that combinatorial sum directly. I just used the fact that this is the sum of a bunch of random variables, and I broke up the sum, and life was much easier, okay? Okay, so comments or questions about this? All right, so one of the things I'm sure you've heard of in the same breath as the mean of something is the standard deviation or the variance, right? Those two things are kind of the key properties that really characterize a distribution, okay? And so let's talk about what does that mean, right? So if I look at this kind of important special case, so kind of a important special case of this kind of discussion is the variance of a random variable. And intuitively, the variance is something that tells us kind of how much spread or uncertainty there is in the outcome of the random variable, okay? So it's kind of like, you know, a measure of how far do we expect x to be from its mean. So for example, you know, here are a bunch of PMFs, all of which have mean 0. Okay, so this is a constant, right? I have exactly 0 all the time. So certainly the expected value is 0. Or I could say I have a probability of 1/2 of getting -1 and 1/2 of getting +1. The average value, again, is 0, right? Expected value is 0. Or I could have something like, you know, way out here at -10 and +10. The same 1/2, 1/2. This also has expected value of 0, right, centered around the middle, but intuitively I have a much larger kind of spread of possible values, right? And finally, I could have something like this. Let's suppose that I have, you know, a bunch of small arrows like this, each of which has height 1/9, right? So maybe I go from -4 to 4. Sorry, my paper's getting, I guess you guys can see it. So basically here, this is like a uniform distribution on 9 values from -4 to 4. And again, if I look at the expected value of this, it's centered in the middle, so I get an expected value of 0, right? So all of these PMFs have exactly the same expected value, but intuitively they have very different properties, right? They have very different variances. So how can we kind of quantify that intuition? Well, the property that we're going to use, or the definition we're going to use, is the variance of x. This is the expected value of x minus the expected value of x squared. Kind of confusing because there's lots of e's and lots of x's, right? So I can make this a little bit more palatable maybe, where mu is the mean, right? So this is like saying, you know, on the average, how far do I expect myself to be from the mean of the distribution? And this gives a sense of the spread of a PMF. Right? So kind of intuitively, you know, this has the lowest variance. This should have variance 0 because there's no uncertainty at all. This should have higher than that. This should have higher than that. This is probably somewhere in the middle between these two, right? How spread out are these values? So let me just pause and say that I can kind of decouple the terms here. So the expected value of x minus e of x squared, let me just multiply that out. I have x squared minus 2x e of x plus e of x squared. And now I could say, okay, well, I'm going to take this apart with linearity. Now what's going to happen here? Actually, before I do that, let me just kind of do this one at a time. Looks complicated, but again, you know, from this perspective, right, this here, this e of x is just a constant, right? It's a number. There's no uncertainty about it. It is a fixed number, right? So from the perspective of the expected value of that number, again, it's just a constant, right? So this is kind of like, you know, these underlined things are just like constants that I can take out. So I have e of x squared minus 2 e of x times e of x again, plus e of x squared. And so what I get is e of x squared minus e of x squared. So this is really important because this is often a handy way to compute the variance easily. And it's really key to know that these two things are not the same, right? So the first term is something that you have to compute, right? You have to crank it through the formula for expected value, right? The second term is a constant squared, right? I mean, it's a rookie mistake, and I see it all the time on homeworks and exams to assume that these two things are the same, but they're not, right? This is like some function of x that I have to worry about, and this is something else. Let me just do a couple of examples to make this more concrete, okay? So for example, let's suppose that I have my Bernoulli random variable again. Let's remember that that's like saying I have 0 with probability 1 minus p, 1 with probability p. We learned from before the expected value of x was just p, right? We calculated that before. What is the variance of x? Well, I'm going to use my definition, and in fact, I'm going to use this form of it here, right? I'm going to say that's like saying I have the expected value of x squared minus the expected value of x squared. So we already know what the second term is, right? Because I already just computed it. This is just p squared, right? But I don't know this, so I have to compute it, right? E of x squared, right? That's like saying I have, you know, 0 squared times the probability of getting 0 plus 1 squared times the probability of getting 1, right? Let me be a little more specific. That's like saying I have the sum from k equals 0 to 1 of k squared times the probability of getting k, right? So what do I got? I got 0 plus p. So I computed now the expected value of x squared is equal to p. That means that my overall value here is p minus p squared, which is a different, you know, I could just say like p times 1 minus p. Right? So that's the way I would compute the variance for a simple example, okay? And I can definitely see, right, that this was equal to p, this was equal to p squared, right? So they're not the same thing. Let me do another example where I use some real numbers to make this a little more concrete. So let's go back to our game, right? So let's go back to the variance for the game that we were playing before, right? So there I had a PMF that looked like it was 1/8, I would give you $0. It was 3/4 that I would give you $1, and it was 1/8 that I would give you $10, right? That's what we kind of boiled it down to. So we talked about before the expected value of playing this game was $2, right? what is the variance of this random variable? Well, I'm going to do this in two ways, right? So way number one is using this formula e of x squared minus e of x squared, right? For this, I have to compute the front part, and usually whenever you're computing the variance, you already have the other part, right? So I'm going to have this minus 4, right? But what is e of x squared? I have to compute it, right? I'm going to have 0 squared times the probability of getting 0 plus 1 squared times the probability of getting 1 plus 10 squared times the probability of getting 1/8. I'm probably getting 10, right? So I get 0 plus 3/4 plus 100 over 8, which is 53 over 4. And then my variance of x is going to be this thing minus 4, which is going to be, I guess, 53 minus 16 over 4 is 37 over 4. Okay. So that's one way to do it. I kind of plug and chug, crank it through, right? Another way that I kind of like to think about it too is that, let's remember that here, this 2 is where I found my expected value to be originally, right? So I could also think about it directly by saying another way, which is that the variance of x is the expected value of x minus e of x squared, which is, in this case, it's the expected value of x minus 2 squared, right? That's my, mean in this case. And so then I could basically say, okay, well, for each of these possible outcomes, how far am I away from 2, right? For 0, I am 2 away from 2, right? So I have 2 squared times the probability of that happening. Here, I'm 1 away from 2, so I am 1 squared times the probability of that happening. And here, I am 8 away from 2, and there's probably 8 squared of that happening. So what do I get? I get 1/2 plus 3/4 plus 8, which is 9 1/4, which is the same 37 over 4 that I got earlier, right? So two ways of solving the same problem. In this case, actually I think this is a little bit easier than doing it the first way I did it, right? But either way will work. So just different ways of thinking about the same problem. So let me pause and ask questions. Yes? Well, since I'm squaring it, everything is always positive inside, right? And that's important. The variance is always positive, right? It's got to be, because it's the expected value of some positive quantity. So if you get a negative number for the variance, you did something wrong. And that's a good sanity check, right? If you go through this method and your number is negative, then you better go back and recheck that you did it right. Other questions? Okay, so let me just say a few more things. So one is that basically, again, the intuition here is that the, the variance, higher variance kind of corresponds to kind of a higher, kind of a spread of values, more uncertainty. You will also see this notation sometimes, sigma of x. That is what's called the standard deviation. And so if you've ever done any sort of data analysis, you've definitely seen the standard deviation before. The standard deviation is defined as the square root of the variance. And so a lot of times you'll talk about the mean and standard deviation of a PMF. Or you can talk about, in kind of data analysis, the mean and standard deviation for a set of data, and those are kind of related to the same thing, okay? Another thing that you may see, just to complete my thought, you know, to compute the variance, we needed to have the expected value of x squared. This general quantity of e x to the k is what's called the kth moment of x. And if I subtract off the mean before I do the expected value, this is called the kth central moment. Right? So, you know, the variance is basically the same as the second central moment. And in some, you know, extreme cases, you may be computing higher order central moments, right? So, I mean, not to belabor the point, but certainly it's possible to have two distributions that have exactly the same mean and exactly the same variance, and I would distinguish them further by looking at, for example, these higher order moments, right? They might have different values for e of x cubed or e of x fourth, right? And some of those higher order moments have names, right? So if k equals 4, you have something called the kurtosis, right? But for our class, mean and variance is basically what you have to worry about. And so I guess one more thing I want to say is that, you know, I'm not expecting you to, you know, so I derived a bunch of stuff in class just because I think it's important to know where things come from, right? But when it comes to working problems or doing exams, there's definitely, you know, tables of these expected values in the book, right? So I know you probably can't read this if I don't zoom in on it. So let me see if I can zoom. What? One could argue that this touch screen is not so responsive. Okay, so for example, here is a table from the book, right? Important discrete random variables. So, you know, in the table you have kind of like a nice one-shot description of the PMF, the expected value, and the variance, and don't worry about this thing, this is called the moment generating function. So basically, you know, we derived all this stuff in class today, right? Here, this is the binomial random variable, this is the sample space, this is the PMF, this is the expected value, and then this is the variance. So we didn't derive the variance of this today, but we did derive the expected value, right? Geometric random variable and so on, right? So if you're wondering what can I write on my sheet for my exam 1, these are good candidates to write stuff down, right? So I would say you can't go wrong by writing down the mean and variance of all the random variables that we talked about. Don't worry about stuff that we didn't talk about, right? So for example, there's some crazier stuff in the book, right? Like this zip random variable. You didn't hear me say it. You don't need to know it. Uniform random variable, we talked about that, and I didn't derive any of those things. So this would be a good thing to kind of understand. And it might not be a bad exercise for you to figure out whether you can derive these values yourself, right? That's a nice problem. Poisson, negative binomial we didn't talk about. So basically, you know, I think 4 of the 8 things on this list are things that we talked about in class. Let me see if I can zoom, what the heck, zoom back out here. I can tell you that this control panel is no iPhone. Okay. Yes, so depending on the parameters of the homework problem, I may tell you, okay, you have to compute this with the direct definition of expected value. That means I want you to crank through the exercise exactly what we're doing in class. If I say it's okay to use properties, then you can use the properties in the table, right? And it will usually be very clear-cut what the right way to do it is, okay? And some of these things are very difficult to easily derive, right? So for example, if I had more time, I would work for you like the variance of a geometric random variable, which turns out to be doable, but it's a mess, right? So who has time for that? Okay, so I think that's it for today. Any questions or comments?